Engineering College, Principal Dr. G.S. Kumaraswamy, HOD of HNS Dr. Harihara Sudan, and my colleagues. I welcome our speaker, Dr. Muralidharan, Professor, Department of Physics, Tech Engineering College, Tech High Tech Engineering College, Avdi. I also take immense pleasure in welcoming all the participants of today's webinar. Once again, welcome, one and all. Over to Mr. Ganesh.
Thank you, ma'am. So, good evening to all. So now I'm going to introduce about the resource person for our today's webinar. He received his UG and PG degrees in physics from Bharat University, Trichy, and also he has obtained his PhD degree from Anna University, Chennai. He was a senior research fellow in Anna University Crystal Growth Center during the year 2001 to 2004, and also he has done 3 postdoctoral research fellowship in various countries like Korea, Spain, and UK. He has given the invited talk in different countries like Germany, Italy, and Japan. He has published 34 papers in SCA journals and also presented 23 papers in seminar, conference, and workshop. He has attended 4 national and international workshops, and also he is having a very good experience in handling many instruments for doing material characterization. He has been working as a professor in Tech, High Tech, Dr. Rangarajan, Dr. Sakunthala Engineering College since 2012, and 3 students are doing research under his guidance. So now the session is handed over to our resource person. Thank you, sir.
Thank you, sir. Thank you for your nice introduction. At the outset, I thank the organizers for giving me the opportunities to share my research interest and research field to this audience. And also I thank my management and my principal for approving me to present our work on this national webinar. Okay, so today I'm going to present our research on room temperature multiferroics through nano and bulk materials. In this presentation, I'm going to introduce a class of materials called multiferroic materials. A brief introduction about why these multiferroic materials are interesting. What is the problem in getting a room temperature materials, and how we can get through materials like a nanomaterial can achieve the room temperature multiferroic bulk materials. So for this presentation, I'm going to take 2 case studies. Nanomaterials, I'm going to this class of materials called vertically aligned, and these nanostructures are vertically aligned and epitaxially grown on a single substrate and a single epitaxial thin films. Okay. So I'm going to concentrate most of my talk on this vertically aligned nanostructure, and if time permits, I will present our work on the bulk materials. Especially, I will concentrate our results on a special class of materials called orthoferrites. Why these orthoferrites are important, and what are the things we have done already, and we can do a lot more on these kind of materials. I'm going to present this. If time permits, I will spend some time on this class of materials. Okay. So before going to my presentation, I would like to thank my mentors. These are all the people who have groomed me, where I learned research. Most of you would be knowing the Professor P. Ramaswamy is one of the well-known, renowned crystal grower, world-renowned crystal grower, my PhD supervisor, and then Professor Jayavil. I worked in his project, and he is my personal mentor. He is always being helpful to me. And then my postdoctoral mentors, Professor Yuni Jiang, where I started learning multiferroics in during my first postdoctoral position in South Korea, when this field, multiferroic field, was just started booming out. So he's one of the renowned person on this field, multiferroics. And then most of the results which I'm going to present in this talk is are the work which I have done during my stay in Spain with the Professor Font Cuberta. He's another well-known person in the field of spintronic materials, and he is having collaboration with two Nobel laureates, one with who got a Nobel Prize for spintronic giant magnetoresistant materials, and a recent Nobel laureate. So he's such a renowned person. And then Professor Andy Bell, AJ Bell, with whom I learned a lot on the piezoelectric materials. So whatever you are going to see, if there is anything interesting, it is because of these people, my mentors. Okay, I thank them before starting this presentation. Okay, so these fields, these persons influenced me on the research topic. In general, I'm interested in almost all topics of material science, and I'm concentrating on, as I said, single crystal growth right from my PhD. Still, we are concentrating on some work on single crystals. I started my multiferroics during my postdoctoral position. Okay, so that is another interesting field. Still, we are working on the materials on multiferroic materials, and then on self-assembled nanostructures, which I was working during most of the results here are during from this title, self-assembled nanostructures. I will tell you why this is important. What are the important things on this one? And from UK, I learned from why these piezoelectric materials for harsh environments are at present. So these are the works I those influence people, and then now on photoferroelectrics, which is for solar cell semiconductors. So I'm concentrating on my research. I'm doing some work on hybrid energy harvesting and renewable energy. Not only from is it possible to do energy harvesting from more than one source. So these are my research interest, overall research interest. So in this presentation, we are going to concentrate mostly on self-assembled nanostructures and some part of a bulk multiferroic materials. Okay. So the outline of my presentation on the first part, this is my outline. So I'm going to give a very brief introduction about multiferroic materials, and I'm going to introduce what are the deposition techniques they are used. I'm going to concentrate on pulsed laser deposition method, on which most of the films which I'm going to present now are grown. So I'm going to concentrate mostly on pulsed laser deposition method. And then I'm going to concentrate this class of nanocomposites called bismuth ferrite, cobalt ferrite nanostructures. And throughout my presentation, you are going to see some composite structures like these structures. Okay, so I'm going to explain what are the interesting things like these nanostructures, and I will also tell you why this bismuth ferrite, cobalt ferrite nanocomposite is important, very interesting. And then I'm going to briefly explain what are the growth parameters, how we can grow these kind of nanostructures, and how the morphology is affected when we change the growth parameters, and then the stoichiometry, why the stoichiometry of these compounds are important. And I'm going to present some of the functional properties which we have measured, and I'm going to summarize and give you some outlooks on the vertically aligned nanostructures, how it can be improved, and what else can be done more. So before getting into the darker, let me, as I said before, we will see why these multiferroic materials are very important. Okay, so in the electronic industries, you know, that we now need high density of memory. So the memory density is increasing in a rapid scale, and now it has almost reached a stagnant position, because the memory bit size has become so small that if you want to one bit, the neighboring bit will get disturbed. Okay, so we need to find some other new techniques if you want to still increase the memory bit for that. And also the density of the devices in IC circuit is increasing rapidly, as we all know. The Moore's law, which states that every 18 months the number of devices in a circuit will be doubled. So for that also, we have reached almost like a stagnant position now, because the transistor size have become so small that the heat produced can disturb. Okay, so disturb the next device. So for that also, we need to have a new class of applications apart from the normal semiconductor. Also, the speed with read and write the data should also increase for the electronic industries. So the current, so it has some limit, speed or limit. Okay. Access time should be increased, and data retention time should be increased, increase the energy consumption. Okay, so the consumption for one transistor now is quite huge when you compare with the density of transistors, which is increasing. So we need to decrease the energy consumption of each transistor. So now we are working on energy consumption like auto-joules per transistor. So for these applications, we need to look for new materials with new functionalities and applications, which is and which should be compatible with the silicon technology, because the semiconductor technology is based on silicon technology. So whatever we are working on other types of materials like oxides, fluorides, and other materials, that should be compatible with the silicon technology, so that the electronic industry we can improve. So for this, at present, the widely used materials are like ferroelectric materials and magnetic materials, metals, insulators, semiconductors. We are working the tuning these properties by doping some other materials. We are tuning all these properties. Okay. So multiferroics are new class of materials by which you can combine these two class of material, ferroelectric materials and ferromagnetic materials. I will come to that in the next one. Okay, so this plant shows the number of publications when you put like the keyword magnetoelectric and then multiferroic. Okay. So this is up to 2008. If you put the multiferroic, the number of publications is keep on increasing. Okay. So when if you see this the multiferroic word, it started around 2000, because this word is coined very recently by people used to call him like a father of multiferroic materials. It's Schmidt. He coined this word multiferroic. Before that, it was called as a magnetoelectric or a ferroelectromagnet. That's why the magnetoelectric keyword was before 2000, and then this multiferroic field started blooming right from 2000 or 1995, and some of the reason why it started from 2000. So this is one of the well-known cartoon for multiferroic materials. You could, some of you could have seen this kind of images. If they would have attended conferences on multiferroics or ferroelectrics or ferromagnetic conferences. Okay, so this group of material where this is the electric polarization, you can switch this electric polarization by applying electric field. Okay, so this is called the ferroelectric materials. So this is the strain parameter. You can switch the strain parameter by applying stress. So this is called as ferroelastic materials. So this parameter is magnetism. You can switch the magnetism by applying field. These are the conjugate field. So this class of material is called as ferromagnetic materials. Okay. So the cross coupling between the electric of ferroelectric materials and ferroelastic known, which is called as piezoelectric. Cross coupling is called as piezoelectric material, and this cross coupling between the ferroelastic ferromagnetic materials are called as magnetostrictive materials. Okay, magnetostriction. So those ferromagnetism, they would have studied about the domains. When you apply magnetic field, the domains will increase. So that is elastic coupling. So this kind of magnetostrictive material, this is also for a few centuries, but this cross coupling ferroelectric materials and ferromagnetic materials, which is called as magnetoelectric effect, is not well known. It is not well known, and it has a tremendous applications in the recent field. Okay, whatever technology we are using, most of them now it is because of these two cross couplings between your electric and magnetic materials, and this was published around 2005 in Science. Okay, so almost the same thing has been explained in this cartoon. The Venn diagram, this is called magnetically polarizable materials, on which a class of materials called ferromagnetic materials. You can have antiferromagnetic or paramagnetic on this region. Okay, or ferrimagnetic, paramagnetic on this region. Similarly, electrically polarizable circle is here, and then on which ferroelectric is a part of electrically polarizable material. The ferromagnetic and the ferroelectric materials, you can switch the polarization by applying that conjugate field, and other materials like paramagnetic or ferrimagnetic can't do that. So that's the difference, main difference between your other polarizable paramagnet and ferromagnet. Similarly, paraelectric and ferroelectric. Okay. So this class of materials, okay, where this crossover between your ferromagnetic and ferroelectric materials are called as multiferroic materials. Okay, so this is called as this region is called as multiferroic materials, where you are having both your ferromagnetic properties and ferroelectric properties. Okay, so this small circle inside this depicts the magnetoelectric materials. Okay, when magnetoelectric materials, you can have other magnetically and electrically polarizable. Apart from ferromagnetic and ferroelectric, you can also have paramagnetic and paraelectric. Still, it is called as or magnetodielectric materials. We are going to concentrate only on this class of materials called the multiferroic materials, and this region, magnetoelectrically multiferroic materials. This region is a very special class of materials which is most important, and people are concentrating on this class of materials. I will, as I said, these materials having ferroelectric and ferromagnetic materials together is very difficult. Okay, just in this periodic table, we all know that the ferromagnetism comes mostly from this group of elements, mostly from manganese, copper, cobalt, and nickel. And also, if you see the ferroelectric property, it will come from this titanium, niobium, tantalum, and this group of materials. Okay, this is because your for magnetism you need the d orbital should be half filled, okay? And then for ferroelectric materials you need the d orbital should should be 0. D orbital should be empty. So you have exclusion principle. So you throw electric material where is half filled, or you can't have a magnetic um, d orbital is completely empty. Okay, so that is why having a materials with both the ferroelectric and ferromagnets very difficult. And you can also have some properties, ferroelectric and ferromagnetic properties, class of materials called rare earth material have magnetic polarization. It can also have some ferroelectric polarization. We will see one by one slowly. Okay, so again, this graph shows the polarization. Okay, so this is the magnetic polarization, north pole and the south pole. So when your electron spins in one direction, you will have the north pole and south pole in one direction, which is called as a time symmetry. Okay, so if the polarization, if the electron spins in the other direction, you are reversing the time symmetry. Similarly, for electric polarization, you will be having the dipole, electric dipole like this. Okay, so if you want to reverse this polarization, you are reversing the space symmetry. Okay, so if you reverse the space inversion, you are reversing the electrical polarization. Similarly, if you reverse the time symmetry, you are reversing the magnetic polarization, but your electric polarization remains the same. As I said before, for multiferroic materials, you need to break these two symmetries together. That is why these class of materials are very difficult or very rare, quite rare. So this class of material, as I said, gained importance because of in science. They have mentioned one of the breakthroughs of invention in around the year 2007. They say one of the breakthroughs in the scientific invention is the invention of multiferroic materials. From then on, quite a lot of people have started working on this new class of materials called multiferroic materials. Into details, just give a brief history about this class of materials. Okay, as I said, even though people have started working on this one recently, this has been predicted quite a long back, even a century back, like Pericles, which he mentioned that materials should exist where in which you can polarize magnetic polarization by electric field and electric polarization by magnetic field. Okay. So we should remember that the ferroelectric materials were not invented at that time. Ferroelectric materials were invented only around 1920, around late 1920s. Okay. So after the invention of ferroelectric material, there are so many unsuccessful experiments between 1922 and 1937 on these class of materials, magnetoelectric materials, because they have predicted that much of application on these class of materials, but unfortunately they couldn't succeed to grow such a material with both the properties, so it was unsuccessful. And around 1958 they started working on a simple class of materials called perovskite, very simple crystal structure with the general O3. Still, it is very interesting. Quite a lot of this class of material. On this class of materials, they have Smolensky, okay, and they have replaced half of which are giving magnetic property, the ferroelectric, the elements which will give the ferroelectric materials. Because as I mentioned in the periodic table, they have replaced iron which is like which has d orbital half-wealth, with the niobium which has a d0 or empty d orbitals, with a half of iron replacing this one. Okay, on the composite, which is ceramic composites, which give some kind of magnetoelectric application, but still it was not a single compound. This is like a doping of a magnetic ion with a non-magnetic ion, 50%. Okay, so even this one, if you see, this is like lead 3. This one, if you take three elements in 9, this is also a perovskite structure. So all these properties trials comes from the perovskite material. So this was the first single compound on which the magnetoelectric coupling was proved by famous ferroelectric material Le Cross. Okay, so this is the Curie temperature at Néel temperature. In fact, Néel temperature. So this is chromium. Cr2BO4. Okay, so which is antiferromagnetic below 25K. This is Néel temperature. This is the antiferromagnetic, and they measured the polarization, electric polarization, which showed some anomaly around 25K. So they proposed that this material, this electric polarization and magnetic polarization are coupled, so that one polarization affects the other polarization. Okay, so this is, to my knowledge, this is one of the first reported magnetoelectric single phase component. On the case of composites, around almost on the same time, around 1974, working on Bell, they reported on the composites of barium titanate and cobalt ferrite. Barium titanate again is a perovskite material, and cobalt ferrite is a spinel structure. They cooled it, and then they found a composite material on which they have a clear like a pyramidal shape of spinel phase, and then this matrix of perovskite phase. So this was reported in 1974, and after that there was quite a long gap. There was no report on this kind of composites. Okay, so different types of multiferroic materials. Okay, so these are called as single phase multiferroic materials. Okay, so this is the these kind of materials are called as type 1 multiferroic materials, where your magnetic polarization, electric polarization are not related. In this lone pair mechanism, your magnet comes from the A site ion, magnetic polarization comes from B site ion. Okay. And in the material called geometrically ferroelectric material, the arrangement of geometrically frustrates, which induces electricity. If time permits, I will also give some examples on this one. This is another class of. This is called as a charge ordered material. If you take a multivalent material like iron, cobalt, and you prepare a material using these compounds, there is a possibility that charge order between Fe2 plus and Fe3 plus on different layers, that may induce some electric polarization, and the magnetism comes from the Fe ion. Okay. So this class of materials are called as type 1 multiferroic materials, and this group of materials are called as type 2 multiferroic materials, where your electric polarization and the magnetic polarization are related. One polarization affects the other polarization. So that means around one transition temperature, for example, if you have a ferroelectric transition temperature, your magnetic polarization should get affected. That means your magnetic polarization should change on that temperature. your a special arrangement of spins can induce electric polarization. Okay, so this kind of spin-driven mechanism, and I'm going to give an example on the bulk materials on this class of materials, and also these are some other class of materials where one kind of a magnetic polarization affects the other polarization, and this graph shows the polarization of a different class of materials, and then the lone pair materials. This class of materials has a very high polarization, around one of the highest known polarization so far, around 90 microcoulomb per centimeter square on bismuth ferrite. On this material, bismuth ferrite. That's why people there is quite a lot of work on this. Especially interesting material, bismuth ferrite, because it is antiferromagnet. You can make it as a ferromagnet, and it has a very huge electrical polarization, like 90 microcoulomb per centimeter square. And then you can also have the multiferroic property on heterostructures. So these are different kinds of heterostructures you can grow. This is called as 0-3 0-3 structures, where you have one you are taking two components, and one component will be on the 0 dimension, and the other component will be on the 3 dimension. This is called as 0-3 combination. This is called as 2-2 type of heterostructures, that superlattices, thin films of different layers can be grown. And also there is a one more class of materials called vertically aligned nanostructures, where you can have one-dimensional rods aligned like this on a matrix. So this type of materials are called 1-3 type of materials. I'm going to concentrate these type of materials. I will tell you why this is important. Okay. So as I said before, I'm going to on bismuth ferrite, because it's very interesting, having around 90 microcoulomb, which is quite huge. On the bulk, this is antiferromagnetic alignment of space. But if you grow as a thin film, you can have a product with a huge elevation. So people start on thin film or nanoparticles of bismuth ferrite, where you can have a ferromagnetic polarization. Okay. And then this is one of the first reported paper on science on this multiferroic nanostructures. Okay, so this is on epitaxial thin films on barium titanate cobalt ferrite, grown on STO substrate by a well-known group from Berkeley called Ramesh group. They are one of the world leaders on these kind of materials. They have grown this barium titanate cobalt ferrite. This is on strontium titanate substrate. This is the strontium ruthenate. If you want to measure the electrical properties, you need a bottom electrode. So this will act like a bottom electrode, over which it shows the barium titanate over 2 peak, and then cobalt ferrite peak. So this is a epitaxial film, and these are all substrate over 1 and over 2 peak. There are no other peaks. So this is quite epitaxial. Epitaxial means it is a single crystalline materials. And this shows the morphology of the film, and it has quite a lot of nanostructures, particularly aligned structures on the top surface. A from image of that one. So this is the TEM image. So you can clearly see the spinels here, cobalt ferrite spinels, which are arranged as rods on a bismuth, barium titanate matrix. On a TEM image, you can clearly see spots of barium titanate and cobalt ferrite. So this implies these are all single crystalline, highly pure thin films. So they can measure the ferroelectric hysteresis loop. Also ferromagnetic loop. As I said, if you this is the temperature and magnetization. As we all know, the Curie temperature for barium titanate is around 120 degrees centigrade, which is around 390 Kelvin. Okay, so around that there is a change in the magnetization. So this shows that the electric polarization and the magnetic polarization on this kind of a material is coupled together. This is their measurement without on a simple cobalt ferrite thin film. It doesn't show any anomaly like this. So on nanostructures, these two materials are coupled together. Okay. So around 2005, they have reported on the same group. They have reported on bismuth ferrite. Cobalt ferrite. Okay, instead of barium titanate, they have replaced that with bismuth ferrite. I will tell you, as I said, is one of the very important and which has a very interesting properties. And so they wanted to replace barium titanate with bismuth ferrite, because bismuth ferrite is a room temperature ferroelectric, and this is one of the very famous MFM image. This is the MFM image where these black dots are cobalt ferrite nano rods, and the electric field at room temperature, the domains, these magnetic domains can be, this is measured on the same region. If you see for these two domains, which are black electric field, and in magnetic using magnetic force microscopy on the same regions are switched. That means you switch the magnetic domain using the which is quite important. And also they have measured ferroelectricity using piezo force microscopy, and it shows ferroelectric property also. So this material is quite important, because they have achieved at room temperature. You can change the magnetic polarization by applying the magnetic electric field. So on the slides which are going to follow, we are going to explore this kind of material, bismuth ferrite, cobalt ferrite nanostructures. So as I said, so far I have explained about some introduction about multiferroic structures. Okay, so I will quickly pass on the deposition techniques. Okay, so we have used two types of deposition techniques. So you can produce these kind of nanostructures using sputtering, magneton sputtering method, and also we can prepare these films using pulse laser deposition method. In this presentation, I'm going to concentrate on pulse laser deposition, films grown on pulse laser deposition method, and then I'm going to concentrate on this composition, 35% of cobalt ferrite and 65% of bismuth ferrite on a single substrate of 001 and 111 substrate. I will tell you why these substrates are important, why we use these substrates, and then we are also used on niobium doped STO substrate, because this is conductive substrate, single crystalline substrate for electrical measurements. We have used niobium doped STO. STO is insulator at room temperature. When you dope niobium, it changes as a conductor. This cartoon just shows how the pulse laser deposition works. This is excimer laser. You have a excimer laser. Pulses starts target on a target. it produces plasma, and then if you have a substrate here, the thin films can be grown. The thin films can be grown on a different atmospheres, like oxygen. If you are preparing oxides, or if you want to grow metals, you can use argon as a gas, so you can prepare metal also. So these are the growth parameters which we used during our growth. We maintained the oxygen pressure on that one, and then we cooled with this oxygen pressure, and then we changed the pulse frequency with from 2 to 10 hertz, and then this is the growth temperature. We have grown on a different temperatures from 500 to 800 degrees C, and then with a different film thickness from 50 to 200 nanometer. Okay. So I'm going to present some of our results on these data. Okay. So this is the PLD machine which we use in Barcelona, which is a very simple equipment when you see as a PLD. This is the Excimer laser. So we are having a chamber here. So the laser comes, and then we are preparing samples on this chamber at very high vacuum and oxygen atmosphere. So the PLD has some advantages. It also has some disadvantages. I'm not aware of that one because of the time limit. Quickly move how the thin on a single crystalline substrate. Three types of growth modes. So one is called as island. The materials, the atoms island. If it is not a wetting partially wets the substrate, the atoms grow as a island, which is also called as a method. There is another kind of growth called growth. It's very good flat growth. If your material wets your substrates properly, then it will grow layer by layer growth. Okay, most of the thin films, they prefer this layer by layer growth. And if you want to have the nanostructures or island kind of structure, quantum dot kind of structure, they prefer this kind of volume web growth. And there are mixed growth also is possible, which is called as Stransky-Krasnov growth, which initially it will grow layer by layer and then forms islands. So these are the three types of growth methods by which the atoms grow on a single crystalline substrate. So as I said at the beginning, so this is the cobalt ferrite barium titanate nanostructures grown on strontium titanate single crystalline material, and this is bismuth ferrite, cobalt ferrite, and so this cartoon shows on this is the O1 substrate. So if you use this strontium titanate substrate as a O1 orientation, you will have a matrix of perovskite. Okay, in our case, bismuth ferrite, and you will have a column of spinels. In our case, this is cobalt ferrite. Okay. So on a O1 oriented substrate, you will be having perovskite matrix on a spinel nanorods. If you change the orientation, substrate orientation to 111, you will have perovskite matrix. Sorry, spinel matrix and perovskite column. Okay, so the green color is perovskite. So you will have the perovskite column on a spinel matrix. So you can swap whatever nanostructure you want, whether you need a perovskite nano rod or you need a spinel nanorod, just by changing the orientation of the substrate. Okay. So this class of materials on bismuth ferrite, cobalt ferrite, they have switched the magnetic polarization by applying electric field. So this is due to the strain. Okay, so if you apply electric field, as your bismuth ferrite is a piezoelectric material, so that will produce some strain. Okay, so that strain, as it is coupled with a ferromagnetic material, that will induce some strain in the ferromagnetic material, so that will change the magnetization, magnetostriction. Okay, so the key here for the elastic coupling is the key. If these two materials are elastically coupled, you can tune the magnetization with the applied electric field, or you can tune the electric field by the magnetization. So elastic coupling is the key parameter here. Okay, so I'll just skip this one, this slide. So this is a single phase spinel material. It explains why the spinels are growing as pyramids. Okay, so if you on a O1 substrate, okay, so the surface energy parameter which affects, okay, and O1, as I said before, completely and grow layer by layer. So it is layer by layer growth, because on a O1 substrate, the perovskite splits completely. One O1 substrate, the spinels bit partially as an island. So one bit grow as a layer by layer, which forms as a matrix, and another one grows bit partially as a nanostructure. So this is the mechanism on one substrate. If you change the orientation of the substrate to 111, the spinel wets completely and grows layer by layer. That's why your spinel grows as a matrix, and then your perovskite wets partially, and then this grows as a island growth. That's why this forms as a nanostructures in a 111 oriented substrate. So now I will move to the second part of bismuth ferrite cobalt ferrite growth parameter. So these are our data on a O1 substrate. This is the X-ray pattern, complete X-ray pattern on bismuth ferrite cobalt ferrite nanostructure. So these are all the largest peaks or the substrate peaks, and this is the enlarged portion of this region. Okay, so you have a substrate peak here, and then perovskite region over to this is the strained perovskite, and then the relaxed perovskite. So you are having two strained regions here, perovskite and cobalt ferrite peak. So this shows that they are all epitaxial. There are no secondary phase. So this is the X-ray plot where you see this is the perovskite, and then this is the spinel, and which tells that these two materials grow like a cube-on cube growth. Layer by it grows like this. Okay, cube-on cube. Okay, if you change the orientation to 111, if you change the orientation to 111 again. This is the substrate peak, STO peak, and this is you can see there is only one BFO 111 and then cobalt ferrite peak. So this again shows this is epitaxial. But if you see this 5 scan, is a little bit twisted. This is changed its angle. If you compare this one and this one, on the phi angle, the cobalt ferrite and perovskite lies on the same angle. If you see here, on the phi angle, this is twisted. Okay, so this is very quite interesting. Okay, so the structure is something like this. Okay, so the spinel and cobalt ferrite are twisted on 111. It is changed. Okay, or like 45-degree and 111 oriented substrate. This is quite interesting, and people are working on this one. Why this is twisting on a 111 substrate? Okay, so I will just lattice strain part. This is the lattice parameter for bismuth ferrite. Okay, so which is the relaxed the bulk lattice parameter is 3.96. if you take cobalt ferrite, the bulk lattice parameter is around 8.3, and this is the substrate lattice parameter, which is 3.5. So if you see the lattice parameter of perovskite is larger than the lattice parameter of. So if this was epitaxially, so that in plane compression. So on in plane, this 96 should come to 3.90. This lattice compress this bismuth ferrite so that it will. So in plane compression should happen. There is an in plane compression that of plane on C axis, there should be an expansion because the volume should be maintained on a unit cell. Okay, so there should be an expansion here. Okay, so that is what is expected. Okay, similarly, if you take a cobalt ferrite, which is lattice parameter is 8.3, so if you take two cells of strontium titanate, still 8.3 is larger. So in cobalt ferrite also, you will have the in plane compression if it grows alone on a strontium titanate, and out of plane expansion, elongation. So this is what is expected. But if you want to grow together, if you want to put these two together on a single substrate, so there is one more interface, additional interface here between your bismuth ferrite and cobalt ferrite. Okay, so that's what is shown here. So if you want to put one more two firm perovskite and spinels together, you are creating one interface here, additional interface. This should be either coherent or semi-coherent if you want to have this as a epitaxial films. Okay? So we should not only see the lattice misfit of a spinel and substrate, or a perovskite and substrate, you should also see the spinel and perovskite lattice mismatch. So this also one of the important parameter on this kind of vertically aligned nanostructures. Okay. So put this together. So this is the lattice parameter which we measured from our X-ray plots, which I shown before. So this is the bulk lattice parameter, C-axis, that is out of plane. So this lattice parameter. So you see these are all compressed. Okay, on both the OO1 and 111 oriented substrates, the cobalt ferrite is compressed. It is not as we expected, elongated. Okay. So on the other hand, if you see the perovskite, it is either relaxed or almost on the same as a bulk. So this shows elastic coupling is occurring between this bismuth ferrite and the cobalt ferrite. So if you want to accommodate these two structures on a single phase, these two are elastically coupled, and this bismuth ferrite pulls this cobalt ferrite, and that's why this is compressed. Okay, so now we have proved that there is elastic coupling occurs between these two structures when you grow these together. Okay, so that's one of the important results we have published on Journal of Applied Physics. Okay, so this is the morphology. The morphology of one substrate, which is grown at 600 degrees C, and the thickness of the film is around 100 nanometer. So you can see clear matrix kind of thing, flat thing, which is perovskite, and then dots which are spinels. Okay, so conventional view. So you could clearly see the spinel structure on a matrix of perovskite. On the other hand, on a oriented substrate, you can the bismuth ferrite grows as a pyramid matrix of spinels. Okay, so this is the image. Okay, how the morphology changes with the different temperature. I don't want to get into of this one. Maybe in the next show you. Okay, why this growth temperature is important. So this tells this is the WDS plot, and there is a wavelength dispersive spectra, okay, spectroscopy of bismuth ferrite, cobalt ferrite. So this is the growth temperature. So if you increase the growth temperature, your cobalt ferrite cobalt to iron ratio, okay, your cobalt to iron ratio remains constant. Okay. But on the other hand, the bismuth to iron ratio is suddenly drops around 650, because bismuth is one of the highly volatile element. So if you increase the temperature, you will lose bismuth, and your full will have a very low bismuth content. So the ratio between bismuth ion will decrease. Okay? So the growth of these bismuth ferrite, it cannot grow beyond 650. This depends on the chamber. Somebody can report around 650. Somebody, it depends on 700. So for our chamber, we have optimized that the growth stoichiometric growth temperature for bismuth ferrite is around 625, and if you go beyond 650, you can clearly see there is a bismuth loss. So this is the backscattered image. The dark one here is the cobalt ferrite spinels, and the white one is the bismuth. This is the growth temperature. So if you increase the growth temperature, you can clearly see here there are no white region. That means you have lost almost all bismuth, and then only cobalt ferrite axis. Okay, and also this one is shows how it varies with frequency, growth frequency. So if you increase the frequency, you can clearly see there was this cobalt ion ratio remains constant, but this composition ion started increasing. That means you are losing bismuth. Okay, so again, the optimized frequency for growth is around 5 hertz. Okay, so we have a very narrow growth window for growing good bismuth ferrite with a very narrow frequency and a very narrow temperature range. That's why growing these type of growing a bismuth ferrite is very difficult. Okay, fine. So this is the TEM image, the cross-sectional TEM image. You can clearly see the vertical columns with the bismuth ferrite matrix. Here the important thing is we also found some 111 pin as an interface. This was done by Toulouse Benedict group on our samples, our collaborators. Okay, so this is the ELS electron energy loss spectroscopy. So you can similar to your redox on SEM on TEM, you can do E. So you can select you can measure the chemical compositions. Really, you can select matrix region, and then you can see the chemical composition. You can see the bismuth ferrite and cobalt ferrite. There is no intermixing. Okay. This is the magnetic force microscopy. Okay, so this is a case of atomic microscopy. Okay, you can as a magnetic tip. If there is a magnetic then you can do the magnetic force microscopy. So this is the magnetic force microscopy image of your disk CD drive. These are all 0, 1 bits. Okay, so which are all magnetically driven. So if you scan, this is on a non-contact mode. So in a magnetic force microscopy, so your AFM tip will run at a very small height. So if your domains are magnetically aligned on one direction, whether your tip will be attracted or repelled, depending on that one, you can draw the image of your domain. So that's called as a magnetic force microscopy. This is one of the very important and sophisticated uh, measurement. Okay, so this is a MFM image of our sample on an as grown sample on room temperature. Okay, so this is the 2 by 2 micron. So this is the morphology of the surface. Morphology of the surface. So you can see a lot of grains, cobalt-fried grains, which are all magnetic. Okay. And then this is the phase image, which is MFM image. You can see clearly see that some domains are oriented on the up direction, and some domains are oriented on the down direction. A cartoon is shown here. Okay, on these domains, some are oriented on this direction, and some are oriented in the down direction. That's why you can see the dark and the bright images. So if you do a line scan on this topography, so these are all columns here. So these are all columns. You can clearly see that some columns are oriented down, and some columns are oriented up. That means on as grown samples, we have shown that the rod, the nanostructure alone are magnetic, and they are randomly oriented either up or down. So this shows that your rods alone are magnetic. Then as I this one, this is as grown sample. Okay, so if you magnetize your sample with like 1 Tesla, you can switch all the magnetization to one direction. Okay, so this is again the topography, and then this is the phase image. Okay, so you can clearly see that all the rods are oriented in one direction. And what we did is we changed the orientation of the tip. Okay, so we changed the tip magnetization to minus, and then we scanned almost on the same region. You can see here, this is almost on the same region. Here, almost all the domains are looking like a bright. Okay, so this proves exactly that domains are the pyramids magnetic. Okay. So this piece of force microscopy on our sample. This proves that this is a samples. Okay, so this is like you apply field like a plus 12 volt, and then you with applying a minus 12 volt. Okay, so you can switch the domain. So this is after after 5. Okay, so that means your ferroelectricity in our films. We have proved that the ferroelectricity is robust. And then this one is again you can switch like a minus 12 volt on this region, and then plus 12 volt on the other region. So this shows that it is a ferroelectric, and then your MFM image shows that it is a ferromagnetic. So we have combined together, and we have shown that it is elastically coupled. So we have and all these measurements were done at a room temperature. So we have shown that these multiferroic nanostructures are room temperature multiferroics. So this is the macroscopic magnetization measured using BSM. So here the easy axis is the out of plane on the OO1 substrate. The EC axis is out of plane, but when you change the orientation of the substrate, the EC axis changes from out of plane to in plane. Okay, so this is the VSM image. We have also measured the MOPE magneto-optic tear effect that also shows a similar property, magnetization on the surface also. It is the same. The EZ axis changes. Is the dielectric macroscopic dielectric measurements. So we put some minute platinum electrodes, and we could do impedance analysis using needles. Okay, I'm not going into the details of this one because of the time constraint. Okay, so I will omit for the present this one. This portion also, as I said, strain is one of the main parameters. Your lattice strain and then the strain between these two composites of the spinel and cobalt composite is very important. So strain tuning is also very important, and we have done some work on strain tuning. And I will just omit these things. I will just introduce about this class of bulk materials on this class of materials called orthophorites, and then I will close the chapter. Okay, so I will just quickly skip this part. Okay, so on the bulk materials, I will just introduce this special class of materials called orthophorites. Why these orthophorites are important? Why what we are doing now, and still people are working on these kind of materials. Okay, skip this. Okay, I will skip this. Okay, so I will close with this introduction on orthophorite materials. So orthophorites is a very interesting class of materials. Again, it's a very simple structure. It's a AB perovskite structure where A site is done on rare earth ion, and B site is a ion. Okay, so that's why rare earth orthophorites because it takes the crystal structure of orthorhombic crystal structure called as orthophorites. There are two magnetic ions. Rare earth, as I said in the periodic, your rare earth like a gadolinium or niobium, europium produce a magnetization. So rare earth can be a magnet. Ion also can have demand. Okay, so the most interesting thing on materials, these are all antiferromagnetic materials. Interestingly, these antiferromagnetic are not a proper antiferromagnetic. These are called as a canted antiferromagnetic because the spins are slightly turned, so that will induce ferromagnetic moment here. So the ion ions on different lattices are not anti-parallel, but they are slightly twisted, so that will induce ferromagnetic component on one direction. Okay, so this is the temperature scale, and above a certain temperature, these are all antiferromagnetically oriented. Okay, so your ferromagnetic component is on this direction. If you cool down, if you reduce the temperature, the most interesting thing is the spins, the ion spins start rotating spontaneously. Okay, so that's very important. Okay, so that is called as spin reorientation. Okay, so this region, so if you keep on cooling at this temperature, the spins start reorienting from one crystallographic axis to another crystallographic axis. So if you see on this cartoon here, the ferromagnetic component is pointing along over one direction above this spin reorientation temperature. But if below this here the spin reorientation starts, and here the spin reorientation ends. Okay, this ion spins completely changed now. Now the ferromagnetic component is along the 1 direction, crystallographic direction. That means it has the ferromagnetic component as a changed its crystallographic direction. This will endure spin orbit coupling, because if the spins and rotating the crystallographically, that should have some sort of coupling with your lattice. So we thought that this is a very good class of materials for multiferroics. Type 2 class of multiferroic materials, because your dielectric constant is based on the crystallographic lattice movement, and here the spin is moving. So this is one of the very important class of materials where we can induce this type 2 type 2 type of multiferroic materials. Okay, so this is the phase diagram which was reported a long back in 1969. Which is having a very rich phase diagram, magnetic phase diagram. So this is the Néel temperature, which is around 675 Kelvin, because the Néel temperature is because of the ion and ion interaction. So there won't be any great change in the Néel temperature, but the other phase changes here, the spin reorientation temperature, and then something called compensation temperature. All these many interesting phase changes on this class of material. And then there is one material called ferrite, okay, where your spin room temperature. So this is a very important material. So a lot of people working on this very important material. Like we are also working on this samarium. Right, spin reorientation is above the room temperature. See any coupling between your magnetic station and spin, we could get a room temperature type to okay, so if you see here, this is the spin reorientation. This is around 450 Kelvin. So you should switch this to around room temperature. So there are quite a lot of work going on this side. So with this introduction, because of our time constraint, I'll just end this talk. Okay, so I will end up with these are all some of our studies on the bulk materials. Okay, so you can produce room temperature multiferroics on this rare earth orthoferrites by combining two rare earth orthoferrites, or by doping some elements with some again ferrite. So with this, I want to conclude with the quote, famous quote. Still, there is plenty of room on this multiferroic class of materials for room temperature multiferroics. Okay, with this, I conclude. Thank you for your participation. I thank the organizers. If you have any questions, doubts, I'll be happy to clear. Thank you.
Thank you so much, sir, for the excellent presentation. Hope that participants would have gained and enjoyed your presentation, sir. There are some 6 questions are there, sir. So shall I read out the questions?
Sure, sure.
First question, sir. Could you please explain the major differences between magnetoelectric and multiferroic materials?
Yeah, as I said in the first slide, and the for a magnetoelectric material, you don't need a ferromagnetic and a ferroelectric material. You can have a paramagnetic material, but still you can have a change in the dielectric constant, which is called as a magnetoelectric. Magnetodielectric materials. It is not a ferromagnetic. For example, take a chromium oxide. This is not a ferromagnetic material, but still it is called as a magnetoelectric material, because the dielectric constant changes at the magnetization changes. Okay, but for the case of multiferroic materials, you should have both a ferromagnetic and a ferroelectric. So you should be ferromagnetism material should be polarization should be switchable with the magnetic polarization, and then ferroelectric polarization with the multiferroelectric field. So for multiferroic materials, it should have both ferromagnetic and ferroelectric. For a magnetoelectric material, it is not necessary that it should be ferromagnetic and ferroelectric. You can say in a general way that all multiferroics can be a magnetoelectric. Not all magnetoelectrics can be multiferroic materials. I hope I have answered.
Okay, thank you, sir. Next question.
Thanks.
Which one is a better deposition technique for making thin films and why?
This is an interesting question. Okay, every deposition techniques advantages and some disadvantages. Example, if you take MBE, you can even put like atom, so you can grow thin monolayer or unit cell wise. One of the best like or ALD deposition is another important deposition techniques. But if you compare MBE is quite expensive compared to PLD, and PLD is quite expensive when you compare with sputtering, and the sputtering is quite expensive when you compare with some other thin film method. So you need to compromise a bit. So we cannot say this method is thin film method is a best method to grow this kind of. So you need to compromise for that one. So whether you need a very thin mono unit cell wise, or you need a bulk property. For example, if you want to study about the interface and then unit cell property, you can't do it like a dipping technique or some other low cost thin film coating techniques. Or you need to grow for MB. Okay. So you need to compromise. You can't say that this method is best. So that's my answer.
Okay.
So every technique has its own advantages and disadvantages.
Okay, sir. Thank you, sir. Next question. Is there any changes happen while changing hard type of magnetic material into nano size of the same material?
Is there any change in?
Changes happen while changing hard type of magnetic material into nano size of the same material.
Surely there will be some change. When you change the domain size from bulk to nano, your magnetic properties will get affected. So there is a critical domain size that's called a super paramagnetic material, and there are quite a lot of interesting reports. Even non-magnetic materials, if you go like a nano size, it can show ferromagnetic properties. So surely it will show some change when you do on a nano size.
Okay, next question, sir. For a magnetic system, which one is best, PLD or sputtering? Which type of target materials we have required for magnetic thin film deposition?
As I said before, you can grow not only magnetic material, any type of material on both sputtering and PLD. So you can grow magnetic materials like bismuth ferrite, cobalt ferrite, or nickel ferrite, whatever magnetic material on sputtering. For sputtering, you need a large target. The growth rate is slow. On PLD, the growth rate is high, but there are some advantages on sputtering also, and there are some advantages on PLD. So you can grow on both the thin film techniques. Can grow for our composition, especially when I consider this nano composites. I feel pulse laser deposition is the better one than the sputtering, because the growth rate affects the interface property. Okay, the coupling, the elastic coupling. So I feel that PLD is a better option for this kind of nanostructures. Reports on sputtering also. Okay.
Last question, sir. How should we take care about column and matrix orientation while deposition of sample?
I don't know whether I have said it or left. Forget. Things are spontaneously arranged. That's one of the interesting thing. Okay, so these cobalt, right? As I explained in the growth mechanism, spontaneously. You are not forcing your perovskite on one crystal structure and cobalt ferrite to be a crystal structure. This is a spontaneous. So if you the orientation of the substrate, crystal orientation substrate, as a because of the growth mechanism, your spinel rod like on a 001 substrate because of the growth mechanism. The only thing you should take care if you are working on this type of nanostructures, two component nanostructures, is these two crystal structures should be compatible. If you take a spinel and a perovskite, these two have some similarities, so they can grow compatibly on one substrate. So that you should take care on a compatible substrate and a compatible two crystal structures. If you take a completely different crystal structure with a perovskite, then it is difficult to grow such a kind of elastically coupled nano composites. So that you should take care of.
Okay. Thank you so much, sir, for clearing the doubts. Now, let us end the session by vote of thanks. I deemed it
Thank
a
you.
great honor and a privilege to propose the vote of thanks on this wonderful occasion. First of all, I would like to express my profound gratitude to our management for their encouragement and for providing an opportunity to conduct the webinar on room temperature multiferroics through nano and bulk materials. I would like to propose my special hearty thanks to our resource person, Dr. R. Muralidharan, Professor, Department of Physics, Welltech High Tech, for making excellent presentation and making this webinar interesting and meaningful. Thank you so much, sir. I would like to express my special thanks to our HOD, Dr. R. Harivarasuvan, for the moral support and guidance. And I'm happy to express my thanks to my department faculty members and special thanks to Mrs. Sangeeta ma'am and Mrs. Jayachitra ma'am for their valuable contribution towards the webinar. Finally, I thank the participant of this webinar for their cordial cooperation to make this webinar a grand success. Once again, I thank one and all. Thank you so much, sir.
Thank you, ma'am. Thank you for giving this opportunity.